Welcome to the Explainer. So, today we're diving into the hidden intelligence that literally powers the industrial world. We're talking about the control of induction motor drives. These are the systems that allow incredibly heavy machinery to move mountains, but with the precision of a watchmaker. If you've ever wondered how that flawless, controlled motion is actually achieved, you are definitely in the right place.
All right, here's our roadmap for this explainer. We're going to cover 1. Anatomy of electric drives. 2. Selecting the right motor. 3. Induction motor core principles. 4. Speed control and starting. And finally, 5. Closed-loop control systems. Let's get right into it.
Section 1. Anatomy of electric drives. To really wrap our heads around the engineering here, it kind of helps to think of the system like a biological body. So there are 5 core components, right? The electric motor, that's the muscle, providing the raw physical force. Then you have the power converter. This could be a rectifier, a chopper, an inverter, and this acts like the digestive system. It formats the raw electrical energy from the power supply into a form the motor can actually use. Next, the controller. That's the brain. It constantly monitors the variables and matches the motor's output to the task at hand. And finally, the load. That's the actual physical burden the whole system has to move.
Now, here's what's really fascinating. The mechanical load completely dictates what the system needs to do. Engineers meticulously categorize these loads. For example, if you're running a hoist or a pump, the power requirement linearly depends on its speed. Pretty straightforward. But if you're dealing with fans or propellers, the torque is proportional to the square of the speed. That's a totally different parabolic characteristic. And then you have things like milling and boring machines, where the power is completely independent of the speed. Why does this matter? Well, mismatching your power to your load type isn't just inefficient, it's a great way to absolutely destroy your own factory equipment.
Moving right along to Section 2, selecting the right motor. So, this brings us to the ultimate crossroads of engineering design. Let's contrast 2 major players here. Imagine you need to put a motor in a chemical processing site. If you use a DC motor with its sparking commutators, well, you haven't really built a drive system, you've basically built a bomb. It is a massive, catastrophic fire hazard. Because of that, the induction motor, which operates entirely without those sparking components, is the clear-cut, safe, and robust winner.
Which brings us to Section 3, Induction Motor Core Principles.
Okay, before we get bogged down in any formulas, let's set a solid conceptual anchor. The key term you absolutely need to know is synchronous speed. When we feed 3-phase alternating current into the motor's stationary part, the stator, it creates a magnetic field that actually rotates. And this rotating stator flux produces induced voltages in the rotor purely through relative motion. Now, the rotor wants to oppose that relative motion, right? So to do that, it starts spinning, basically chasing that magnetic field in the exact same direction. But here's the catch. It never quite catches up. That slight difference in speed, that's called slip. And slip is the absolute essential ingredient that allows torque to be produced in the first place.
And looking at this, we can see exactly how fast that magnetic field is spinning. Whether you're calculating for radians per second or revolutions per minute, the speed is directly tied to 2 physical realities. First up, the supply frequency of the electrical current. But look at the denominator there, P. That P isn't just a variable, it represents the actual physical magnetic poles built right into the machine's stator. So the synchronous speed is literally locked to how the machine is physically built and the frequency of the power feeding it. And to really dive deep, engineers actually model this relationship using equivalent circuits. They map these physical realities into electrical components so they can calculate the various power stages, tracking everything from the raw input electrical power all the way down to the final mechanical power output right at the shaft.
All right, Section 4, speed control and starting. Now keep in mind, we need to control the motor speed across 3 very distinct operation modes: standard motoring, plugging, which is essentially rapid braking, and regenerating, where we're actually sending power back to the source. So here's the million-dollar question for industrial engineers. How on earth do we control an induction motor's speed across all these varying modes without sacrificing its maximum pushing power? I mean, if you just drop the voltage, you lose your torque. So what's the clever engineering workaround here? Well, engineers can use a bunch of methods, right? Pole changing, slip energy recovery, or even advanced V/F frequency control. But the method we're looking at right now is rotor resistance control. And man, it's just a beautiful piece of physics. By connecting an external 3-phase resistor to the slip rings of a wound rotor induction motor, we can actively increase the rotor's resistance. And here's the crazy part. Increasing that resistance doesn't change the synchronous speed, and it doesn't even lower the maximum torque. Instead, it physically skews the performance curve. It forces that maximum torque to happen at a much lower speed. So by just keeping the voltage and frequency constant and turning up the resistance, the motor slows down but keeps its absolute maximum physical muscle totally intact. And that brings us to starting these beasts. There are several starting methods out there, like star delta or auto transformer starters. But for phase-wound rotor motors, this exact same trick, adding external resistance, is literally the secret to getting them going from a dead stop. See, when you first flip the switch on a massive cage induction motor, the starting current can be violently high, like high enough to completely blow out your electrical system. But by inserting that extra resistance into the rotor circuit during startup, engineers can safely choke back that massive starting current while simultaneously increasing the starting torque. It gives the motor a powerful, totally controlled push right off the starting line.
But, what about when we want to stop or just get up to speed smoothly? I mean, think about what would happen if you tried to instantly halt a machine that's spinning at 5,000 steps per second. It would literally tear itself apart. There's no way. And that's exactly why we use something called ramping. Ramping is a process where the controller progressively increases or decreases the driving pulses to accelerate or decelerate the motor on a smooth, gradual slope. And this ramping is very commonly achieved using V/F control. That's variable frequency drives, where the controller scales the voltage and the frequency together. This preserves the mechanical integrity of the entire load. No sudden jerks, no broken equipment.
Finally, Section 5, Closed-Loop Control Systems.
So, let's look at how all of this builds into a fully automated loop. This takes a wildly complex algorithm and distills it into a linear, real-time process. Step 1. The brain compares the speed we want, our reference speed, to the actual speed the motor is currently spinning. That generates an error signal. Step 2. A controller uses that error to generate a slip command. Step 3. It takes that slip command and adds it back to the actual speed to figure out exactly what the new synchronous speed should be. And step 4, using that new target speed, it calculates the exact voltage command to feed the motor based on that V/F relationship. The system is just constantly adjusting itself, completely autonomously.
But, of course, every smart system needs safety guardrails, right? In this closed-loop process, there's a really strict component called a limiter. This limiter is constantly watching that slip command we just talked about. Its whole job is to ensure the controller never accidentally commands a slip speed that pushes the motor past its maximum allowable torque threshold. Basically, it acts as a safeguard to prevent the system's brain from ever asking the motor's muscle to do something physically impossible. And we actually see this exact same philosophy in servo motors. As the quote points out, the control circuitry will tirelessly drive the motor to the angle specified by the input signal until the difference is exactly 0. It's this continuous, relentless feedback loop that guarantees the motor reaches its exact destination flawlessly. It allows these systems to handle incredibly heavy loads with, frankly, unimaginable precision. So, from understanding those macro-mechanical loads to the subtle manipulation of rotor resistance, all the way down to real-time microcomputer feedback loops, we've seen just how incredibly sophisticated these drive systems really are. But as automation demands factories that can seamlessly shift between motoring, plugging, and regenerating in a matter of milliseconds, how will the AI-driven microcontrollers of tomorrow push the physical limits of copper and steel? It's pretty wild to think about. Thank you so much for exploring the mechanics of induction motor drives with us today. Keep questioning, keep learning, and we'll catch you on the next explainer.